Welcome. Today we're going to be talking about radiation and health. Radiation comes from lots of different forms. We're going to be talking about the spectrum and what we might expect in terms of health effects. So when we're thinking about radiation, you can think about it from many different sources. So you can think about it from cosmic rays, you can think about radiation coming from soil and plants, you can think about it from just all humans and animals emitting natural levels of radiation, and also some rocks actually give off radioactive radon gas. And so you hear about radon quite a bit. We're going to be talking a little bit more about that as well. So this is one of my favorite images because I appreciate very, very much the electromagnetic spectrum because it really kind of puts into play the wavelengths that we're thinking about and how those wavelengths can give rise to how changes might be expected in various places. So for example, as we're talking about gamma rays, which is, these really short wavelengths, because they're so short, they are able to impact the atomic nuclei in our cells. So one of the things that we want you to kind of keep in mind is the difference between ionizing radiation. So these can produce ionizing effects versus non-ionizing radiation. And so the wavelength of these electromagnetic spectrum can influence these outcomes. So we're going to start with visible light because visible light is beautiful and amazing. So this is around the size of bacteria in terms of how big those wavelengths actually are. And so you can think about it in terms of our beautiful sunsets that we have here in Oregon. And so the reasons that some of these things, as we have this visible light, the distance, the things that have to be scattered, the wavelengths from the sun. So the blue and the green and the yellow, they get scattered as they go through through our atmosphere, and it goes through this really long distance versus the red wavelengths, which tend to persist. So it gives us these beautiful sunsets, especially late in the day, whereas during the midday, it's a short distance. Those wavelengths aren't scattered quite as much. So as we're thinking about some of this, we can think about a couple of different things. So one is there's some new science that just came through. So I'm a big fan of new science. And so even lightning is producing some gamma rays as lightning is hitting, it's sending some positrons down from Earth. So this is a component of antimatter, so it's super awesome. And then the things that we can also keep in mind is as we're thinking about radiation is going to be highest related to at the poles, so at the North Pole and South Pole, and at elevation. So think about mountains and such, because you have less atmosphere for some of that radiation to pass through. So these aurora that you get from the radiation coming from the sun produce these beautiful charged particles that pass through our atmosphere up and over. So as this happens, this is both due to the composition of the particles. So what is kind of being excited and charged, so nitrogen versus oxygen, and then what are those distances? How high above our atmosphere is this actually happening? So then as a result of this, you get these beautiful northern lights and southern lights. So they actually exist on both poles. If you are curious kind of where they are and if you want to be able to see them, so you can go to earth.nullschool.net and you can kind of see where the aurora should be visible at any given time. The other thing that we're going to be talking quite a bit about are fireworks. And so fireworks are, celebrated in our country. However, as we're kind of thinking about some of these things, the reasons that we have these fireworks are because we are burning metals essentially, and other components as well. So the colors that we see are because of what is being burned. And so this is very similar to the northern lights in the sense that we're talking about oxygen and nitrogen being excited down below in our atmosphere. As you burn and excite some of these components, you will get certain colors, and these are celebrated and exploited for fireworks and other things. The downside is that I get a little bit grumpy because a lot of these are going to be heavy metals and they can have health effects. Other things like strontium salts, these exist as naturally existing radioactive isotopes. So it's possible, again, there's not much literature on this, what is this going to look like down the road as we are continuing to do more and more and more of these fireworks? So if you are curious, so I don't want to be show all the downsides related to these. However, we need to keep this in mind. So as we're burning all these fireworks, there's a lot of toxicity related to particulate matter in the air, and it can cause some problems. And so if you are curious and want to go down the rabbit hole, know that there is quite a bit of literature related to fireworks. I'm also, it also produces fire risk. There's lots of noise impacts, especially when it's being used in rural areas where it's affecting wildlife. So, there's some downsides of, the beauty and the pageantry of fireworks. So keep that in mind as you're kind of thinking through some things. Okay. As we come back to the electromagnetic spectrum, one of the things that I'd like you to kind of keep in mind is that, we're able to use the spectrum in order for our health diagnostics. So if we're thinking about X-rays, that X-ray spectrum, those are our mammograms, those are our CAT scans, so computed tomography. So these X-rays allow us to understand what is happening on the inside of our body. They are associated with an amount of radiation. Likewise, PET scans, so that is at the gamma ray level. Your MRIs and fMRIs are in the non-ionizing radiation spectrum. So we're going to spend a little bit more time on those X-rays and PET scans because they're super important. So they are used in radiation oncology a lot. So it is really important that if someone has cancer, that you are delivering radiation to the right place at the right time. So they'll use lasers coming in from different perspectives in order to target the tumor. So it's amazing science, completely beautiful. As we go into these gamma rays, you'll think of a couple of different things. So as we're talking about these atomic nuclei, we're going to be going just a little bit into this, but know that there is a substantial amount of literature behind this. So essentially, as we're thinking about alpha radiation, or gamma radiation or beta radiation, so those are the three types that you'll typically hear. So they have specific components for each. So the thing that I want you to recognize, alpha, beta, gamma radiation. You'll be able to look up those details. Remember those. The reason that they matter is because they can have different impacts on human health. And the different impacts are going to depend on the type of particle radiation. So if we're talking about alpha radiation, for example, it cannot penetrate the skin, whereas beta and gamma can. So you might remember of as you go to the dentist office, they will cover you with these lead aprons, and this is to protect you from radiation effects. So these are a couple of different images so you can see the different ways that these particles can travel through different substrates. So as we're going through and thinking about these things, these are different ways that you can do protections and PPE and the hierarchy of controls. Because they have different impacts and because they can impact the body differently, these are the things that I want you to kind of keep in mind, this table in orange. So for example, if we're thinking about outside the body, like just circulating in air, alpha particles are completely fine. They are not able to pass through human skin. So theoretically, technically, they are not going to be able to hurt you. However, because beta and gamma rays can pass through, know that they can have greater impact for our health. However, if we are starting to ingest, so either food or we start breathing in air, alpha is incredibly damaging because those particles are just in there, just cranking on some of these radiation. So beta and gamma is still dangerous, but not to the same impact, not to the same effect as alpha radiation. The other thing that might make your head explode is like you can think of something like uranium, which is just present in our atmosphere. And as this uranium-238 just decays naturally, it will go through many different nuclides that have different types of particle radiation, so alpha or beta, for example. And each of those have a half-life. And those half-lives simply say, how long does it take for radiation to decay by half? So if we're talking about uranium-238, the half-life is, billions of years versus if we're talking about, polonium-214, you're at like just fractions of a second. My former life is from the lab. So I think about all of these things in terms of how they can be used to study human health. So the things that you will typically hear related to, using radioactivity for science. So you'll hear about tritium a lot. This is simply hydrogen that is emitting beta particles, and you're able to measure some of these things. Carbon-14, so we use that for dating. So you can use it for like trees or when was pottery found. this allows us to really measure the timestamps of certain things. For phosphorus, radioactive phosphorus, that's used for studying DNA. We have the DNA has a phosphorus backbone, so that is helpful for that. And iodine is used for our thyroid. So there are all sorts of different ways that you can kind of use these radioactive particles to study things of interest. The one that you'll probably need to know the most is radon. So this is a colorless, odorless gas. It is a byproduct of radium, and it produces alpha particles. So the reason that this can be a problem is that, so radon is, can be in our homes, that radon can be breathed in our homes, and it can cause a lot of problems, particularly as you breathe it in. This puts it right next to the cells where they can do a lot of harm. This can cause lung cancer, and people can have a lot of problems related to this. So as a result of this, people think a lot about radon, measuring the impacts of that. And so this is the one that is probably highlighted the most in environmental health. So make sure that you understand what radon is and how it works. Because it is going to be different based on what's in the soil. So some of the places have the highest amount of radon, some don't. So it just depends on the geological composition of our soils. So as you're kind of thinking about this is one of an image as you're kind of going through. So you can use these Geiger counters and other devices to measure the radioactivity of various readings. So for example, if you have a high radioactive rock, you wrap it in paper, it's still pretty high, and then you wrap it in aluminum foil. So based on that, what might you expect to see? So we talked about how far things can go through. And so you might be thinking, okay, so it dropped because of aluminum foil, so that's probably D. But there's a spoiler alert in that it is actually E because it doesn't actually drop to 0. So there's still a little bit right through here, so it probably is producing all 3 particles. Okay. As we're thinking about the radiation effects, the amount of radiation and what is being exposed is going to have a big impact on the effects of that radiation, for example. So as we talk about this exposure is cumulative as part of our lives. This radiation can cause problems to DNA repair and lots of other cellular problems. So as we're kind of talking about these things, we're going to be talking about the amounts of radiation. And this can be somewhat confusing sometimes. So as we're thinking about all of these, regardless of the amount of radiation, think about yourself in the context of these hierarchy of controls. So rather than just protecting the worker, if you can think upstream of how to remove the hazard rather than simply protecting individuals, that's what you're going to want to do. As we start thinking about these things, we're not going to go into the weeds related to this, but know that there's different terminology related to how radioactivity is being measured and how it is being used in terms of health. So for example, the old way was curies, now we use becquerels, and some of these, the curies are considered big amounts, whereas becquerels are small amounts. Gray is being used in radiation. So as we are thinking about these things, the one that we use most frequently right now is called sieverts, or microsieverts, millisieverts. So it's just the amount of sieverts. But know that it can be a little bit confusing, and that's okay. So there are full fields that go into this. I mean, you can imagine if you're going to be doing radiation therapy, you need to know how this works. So how radiation is exposed to different biological tissues. There is a ton of math involved. There's a ton of particle physics involved. It is amazing. You don't necessarily need to know that per se of how it works, but know that people know how this works, and it's pretty amazing. I very much appreciate this chart for putting things into context. So again, as we're thinking about various radiation doses and how much a person can absorb, again, this is that absorbed dose is considered in sieverts, and that is a way that we can measure the effect of a dose of radiation and what it would have on the body. Okay. As we're thinking about this, so you'll hear of 1 sievert, and then millisievert. 1,000 millisieverts is the same thing as 1 sievert, or a million microsieverts is the same thing as 1 sievert. So it's just a fraction of scale. So you can see on the left-hand side, as we're talking about these things, here's an arm X-ray, and that is 1 microsievert. If you pull all of those things together from that former chart, now you'll have these 60 microsieverts from that previous chart. And as you start pulling these various doses from various places, you can kind of get a sense of, well, what is a normal amount of radiation and what is an excessive amount of radiation. So as we're talking about some of these things, a chest X-ray is 20 microsieverts. If you are looking at a chest CT scan, we're at 7 millisieverts, and the maximum yearly dose for US radiation workers at 50 millisieverts. If you take all of these, this is that all of the doses in that green chart come down to this 75 millisieverts. And now you can start seeing the difference between what happened with related to Fukushima. You can see what happens related to radiation poisoning and what a fatal dose might look like with and without treatment. So it's an amazing way to kind of summarize these cumulative impacts, if you will. All of those red radiation exposure amounts can be put into 10 minutes next to Chernobyl at the reactor in Russia. There's a lot of radiation. So there are three ones that we typically think of. Pardon me, it's not Russia, it's Ukraine. As we start to think about some of these things, so not only do we want you to know about Chernobyl, but we want you to know about 3 Mile Island, and we know about Fukushima because that happened pretty recently. So there's lots of different ways that we can think about how these work. And as we hear about some sort of nuclear meltdown or nuclear problem, the panic starts to set in. So you're like, well, what is the actual impact related to these things? So here's the radiation where it puts all of those doses together. And then this is one chart that is just stunning and I super appreciate. And then the other thing that I super appreciate is as you kind of think about these different amounts of radiation, you can look at the differences between, say, 3 Mile Island versus Chernobyl in Ukraine versus Fukushima in Japan, and kind of what are those differential impacts in terms of amount of radiation that's released and what people may expect. And so, spoiler alert, Chernobyl is by far the most significant in terms of amount of radiation. And this tells you a little bit more if you kind of just place it into a graph form. The other thing to think about as we are on our planet and we're looking at moving towards space, so there's exposure of radiation in space, which is not surprising. We are closer to the sun, there is less atmosphere. But as we're kind of thinking about these trips to Mars, for example, there are going to be different amounts of career exposure that NASA astronauts can experience. And so it's going to be different based on, body size of males versus females and age. So if you are younger and more in childbearing years, you might want to have a lower dose versus later in life. So, and as we're kind of talking about these different types of missions, like you can look at an estimated Mars mission, the amount of radiation that's expected is over the career exposure limit for a female astronaut who's 25. So there are going to be differential risks for individuals. So most frequently, we tend to think, not most frequently, but often we tend to think about UV radiation in terms of the sun and sun exposure. And so you'll hear about sun exposure and skin cancer quite frequently. So there are 3 types of UVA radiation that you'll typically hear about, again, based on wavelength. So the short wavelength of UVC is the most damaging. It is very harmful to us. However, the Earth's atmosphere typically filters that out and it doesn't necessarily reach the Earth's surface, which is great. So one of the things that you'll hear more frequently about are this UVA and UVB. So UVB can't penetrate beyond the superficial skin layers, but you still have this delayed tanning response and other issues related to UVB. And then UVA is the one that can penetrate deeper into the skin. This has long-lasting problems related to skin cancer. So things to keep in mind related to this. There's a that potentially the clouds are going to filter out. And so because we live in, this is in Oregon, so this is related to melanoma data this was from a grant we put together a while ago. But you can see that the incidence of melanoma in Oregon is, different based on counties. And it's, again, we have a greater population size in this western region. But this is also where we have the most clouds. And as we're having more and more skin cancer in these regions, you have to wonder, is this because we're not wearing sunscreen because we don't think that we're vulnerable to it potentially, or vulnerable to sun exposure because we live in cloudy environments? Is this because people are moving from other regions where they had higher exposure to UV as a child? Who knows? But these are some things that OHSU scientists are thinking about, because there are discrepancies in the geographical incidence of melanoma, for example. The other thing to keep in mind is that as you're thinking about sun exposure and UV exposure, like this is a graph we put together that was just looking at if the latitude on Earth and then the average UV index over a 12-month period. And you can see it's this beautiful curve showing how there's a really nice degree. So if you are closer to the equator, down at this 0 point, you are going to have more UV exposure than, say, closer to the poles. As we go through that, one of the things that pops up is that our bodies have melanin, which help us to protect our cells from ultraviolet light exposure. However, there's been, as we're kind of thinking about, inequities and disparities, we know that sun sensitivity is associated with skin cancer risk. And there's been a long history of assuming that because individuals may have darker skin, that they might not be at risk for skin cancer. And it turns out that's not the case at all. The issue is that these individuals, they can still get skin cancer. They can still experience the damage from ultraviolet light exposure. However, the problem is that these individuals are getting diagnosed at later stages of the disease when it is more deadly. So they have individuals, people of color, have higher rates of skin cancer mortality. The other thing to kind of keep in mind as we're kind of thinking about these things is that individuals, people of color, don't think that they are at risk because that's what they've been told for many, many, many years. So there's this report. So this Fitzpatrick skin type has been used for, for years and years and years and years. As we're thinking about it, they only looked at skin typing for the first, there are 6 skin types, 1, which is the lightest, 6, which is the darkest. They only categorized Fitzpatrick skin types through 1 through 4 for many years. And so as we're trying to think about how do we better describe risk for individuals, talking about things like tanning and burning aren't necessarily appropriate for people with darker skin types. They're not necessarily burning. However, this is through the Eilers paper, but they are experiencing, skin discomfort or irritation, sometimes itching. So the wording that we use for describing sun sensitivity has a huge impact on either perceptions of risk and also how one might protect themselves against sun exposure. So we've spent a lot of time talking about X-rays, PET scans, ionizing radiation, which are all pretty well understood for how they impact the human body. They're generally understood to be harmful to human health if done in excess. Small amounts, we use them for, health diagnostics. However, we're now starting to learn more and more about non-ionizing radiation. And while it's been long expected and thought that they don't have any harmful health effects, we're starting to see some additional ones starting to pop up. So, for example, there's some new data that's looking at using microwaves related to Department of Defense and producing Havana syndrome. So as we're kind of thinking about some of these things, what might we expect related to this? And so I just encourage you to follow the science because we're learning more and more about how all of this works. Enjoy.